So we're starting our last section in chapter 5, which is 5.4, and it's the last set of trig identities that we're going to go over. There are a couple more sections over trig identities in chapter 5. We're just not going to go over them because basically they work the same way. Like you see a new formula or equation and then you apply it to different types of things. So we're going to do this last set, and the skills that we learn from it would be the same, whatever the other identities would be. So here are your sum and difference trig formulas. For your quiz, you will not have to have these memorized. So again, it's mostly just how to use them, when to use them, those sorts of things. So you don't necessarily have to have them memorized. But we do probably want to write them down to have in order to reference as we go throughout some of the problems. So our sum and difference formulas are used when we need to either break apart angles that aren't on our unit circle, or sometimes if we have addition or subtraction inside of it with like a variable or something like that, we can also use these to break it apart. Because remember that sine is like our square root function, like our exponential functions. We cannot distribute them. So I cannot distribute a sign when I have two things that are being added or subtracted, which is why we have to have some sort of formula that allows us to break it apart and simplify it. Do we have those down? Okay. Alright, let's look at it in your table. So this one says to find the exact value of sine of pi over 12. Is pi pi over 12 on our unit circle? No. Okay, so does that mean we can plug it into our calculator? We can't plug it into our calculator? We can. Is that what they want us to do, though? How do I know that's not what they want us to do?
Exactly.
So this is exact value. What would the instructions say if they did want us to plug it into our calculator?
Something.
Put it in your calculator.
Either put it into your use graphing calculator, use graphing utility, round to a specific decimal. What's the other word that we have there? So instead of an exact value, we would be approximating. So it might say approximate the following value, and then we know that we want to plug it into a calculator. So in this case, that's not what they're wanting us to do. So we're needing to apply one of our trig identities in order to be able to simplify that further. And because it's in this section, we're going to be applying our sum and difference formula. But in order to be able to do that, we have to pick two things that are on our unit circle and add or subtract them to get pi over 12. Does that make sense? So like we're trying to pick those u's and v's that were on the previous one that either add or subtract to get to pi over 12. So what do we think? Okay. Is that the only combination that would work? Yes, no, maybe. Does that combination work? Yeah? Is there another set of combinations that would work? So you would have had 6 pi over 12 minus 2 pi over 12. So not quite. What about like 2 pi over 3 minus 3 pi over 4? Does that work?
Yes.
So there's actually several different options that you could use. Okay, but because of how the formula is set up, you would end up with the same answer as long as whatever two you pick actually give you what's in there. Okay, so then we're just going to substitute whatever we decided we were going to use. So in this case, we have pi over 3 minus pi over 4. Okay, and then we just apply our formula. So what's acting as our u in this case? Pi over 3. What's acting as our v? Pi over 4. And then which formula are we using? The sign subtraction one. So we would have sine of pi over 3 times cosine of pi over 4. Now for sine, it's the same operation, so subtraction. So think like sine S, same. Cosine has an O, so opposite operation. And then we would have cosine of pi over 3 times sine of pi over 4. Now, are pi over 3 and pi over 4 on our unit circle? So should we know what sine and cosine of pi over 3 and pi over 4 are? Yes. We should be able to evaluate things from our unit circle. So what is sine of pi over 3, which is also 60 degrees? What do we think?
1 over 3.
So we should have our unit circle somewhere. We need to reference back to it. Then square root of 3 over 2. What is cosine of pi over 4? What is cosine of pi over 3 then? If sine is square root of 3 over 2, what's the other option? 1/2. And then what is sine of pi over 4? Square root of 2 over 2. Now remember that we can multiply, our radicals. And then now, since they have the same denominator, we can combine them. Can we subtract radicals?
No.
What do they have to have in order for us to be able to subtract them? Yeah, which is also called our quadratic cube. So remember that in order for us to be able to add or subtract, the stuff on the inside would have to be the same. In this case, it's not. So then that's our final answer. Which is why, if you plug that into your calculator, you would get a nice, pretty decimal, because square root of 6 and square root of 2 are both irrational numbers. Questions on that? Okay, let's look at another one. So this time we have cosine of 75. So are there two things that we could add or subtract from our unit circle that give us 75 degrees? We 90 what?
90 minus 15.
But it's 15 on our unit circle.
But it's 30 plus.
It is, but in general we want to try and do something that is on our unit circle. So what?
30 plus 45.
We could do 30 plus 45 instead. So what's different about our cosine though formula?
Cosine, cosine, and then sine, sine.
What else? What did I say last time?
They flip the operation.
Mm-hmm. Okay. So we'll have cosine of 30 degrees times cosine of 45 degrees. It's going to be subtraction this time, and then we'll have sine of 30 sine of 45. What is cosine of 30?
1/2.
Nope.
Yeah, just for root 3.
Mm-hmm. What's cosine of 45?
Square root
What's sine of 30? 1/2. And sine of 45. Adds in an extra something.
root 2.
Mm-hmm. Square root of 2 over 2. Which that should look vaguely familiar. Do we have any ideas as to why it looks the same? Do we get the same answer as our last one? Why?
Because it's also 90 minus 15.
Which means they are what? So sine and cosine are co-functions, which means that yes, if I take 90 or pi over 2 and subtract one, it's going to equal the other one. So like what is pi over 12 in degrees? 15. So 90 minus 15 is 75, which means that 15 and 75 are what type of angles? No. Think back to geometry. When I have two angles that add to 90, what are they called?
Complementary.
Complementary
The other
angles. So whenever you have and cosine of complementary angles, they're going to be the same thing. So if I had tangent of 75, what would it equal? Like what trig function of 15 would it equal? So like cosine is the cofunction for sine. What's the cofunction for tangent? Cotangent. So that means that tangent of 75 would equal cotangent of 15. Because they're cofunctions as well. Does that make sense? Yeah. Alright. So let's look at another one. On this one, I want you to find sine and cosine on your own, and then check with your group, and then we'll do the tangent one all together. So for this one, we're looking at sine and cosine of 165 degrees, but I just specifically gave you how I want you to break it apart. So you're going to use sine of 135 plus 30. So sometimes it might give you the way it wants you to break it apart. Sometimes it'll let you pick what way to break it apart. Bless you.
There you go.
have negative here, right? We would end up subtracting. And this would be Do we get answers? Okay. So what's the thing that we need to remember with 135 degrees? What's our reference angle? 45, but it's in our second quadrant, so what does that mean? Cosine needs to be negative. Now, most of these, when we're using our sum or difference, because we're using the unit circle, you're going to have lots of square root of 3, square root of 2s, and 1/2, okay? So that means that it's even more important that you use the right signs, SIGN, so positives or negatives. So we have sine of 135 times cosine of 30 plus cosine of 135 times sine of 30. So you end up with the square root of 6 minus the square root of 2 over 4 for sine. Now for cosine, again, remember that our operation is the opposite here. So you end up with a negative square root of 6 minus the square root of 2 over 4. Yep. Yes, no. Like I said, the big thing to watch out there is going to be your positives and negatives. So then, let's look at the tangent one all together. So we're still going to be breaking apart our 165 the same way. It's just now, which formula are we applying? The tangent one. And what does it involve? Fractions? Yeah, which is okay. So what am I going to have on top? Tangent of u, which is what?
135.
A plus tangent of v, which is 30, divided by 1 minus tangent of u times tangent of v. Well, is tangent on our unit circle? No, but what can we use from our unit circle to find tangent? Sine over cosine. So what is tangent of 135 degrees? Almost negative 1. So notice that both sine and cosine are square roots of 2 over 2. But since cosine is negative, tangent will be negative 1. What is tangent of 30? Well, what is sine of 30 degrees? 1/2. And then cosine is square root of 3 over 2. So we flip. And we get 1 over the square root of 3, which is also square root of 3 over 3. So notice that we end up with the square root of 3 over 3 minus 1 divided by 1 plus the square root of 3 over 3. Can I reduce anything? What do we think? Why not?
Because they're adding and subtracting.
I agree. What does it have to be in order to be able to reduce? Multiplication. But could we simplify that? Maybe. Right now we have like 4 different fractions. So it might be helpful to simplify our fractions a little bit. Notice, what's our denominator on the top and the bottom? 3. So I'm going to multiply by 3 over 3. Because it's going to get rid of those extra fractions. So notice on top, I would just have the square root of 3 minus 3. And then on bottom, we would have 3 plus the square root of 3. So we still can't simplify anything out or reduce anything, but it makes it a little bit nicer. Okay. Now I will tell you, your book is actually going to take it a step further to get rid of the radical in the denominator. So remember, to get rid of that, we would have to multiply by 3 minus the square root of 3, which is our conjugate to the top and the bottom. I'm okay with you leaving your answer like that. However, just know if you're checking your answers in the back of the book, if there's not radicals in the bottom, that's what they did to get rid of it. Does that make sense? But I'm okay with it. So remember that most of the time we like to rationalize things, just like we did up here, right, with our 1 over the square root of 3. But because I have 3 plus the square root of 3 here, I can't just multiply by the square root of 3. I have to multiply by the conjugate, which would be 3 minus the square root of 3. And then you would have to FOIL out the top and the bottom. Yeah, which is it's a longer process. And really, when it's like a single number, it can be helpful for us to rationalize. From here, there's not anything that we wouldn't be able to do with it. So we're okay to leave it like that. Other questions? Okay, so what about this one? What's different?
And, well,
You can use a calculator.
I mean, we could. It still might not give us nice things. But does it look familiar?
Yeah.
What does it look like? So we have been starting with the left side and breaking it apart to get the right side, yeah? But this time we're starting with the right side and we want to combine it to be the left side. Remember, equal signs go both ways, so we can use either one. So because it's sine cosine, that tells us that we're using which of our trig functions? The sine one. And then are we going to have addition or subtraction? Because it's the same operation. So we would have 42 degrees minus 12 degrees, which is what? 30. And what is sine of 30? 1/2. That would be my answer. And so we need to make sure that we can do that with any of our identities. If we're given something that looks like the right side, we need to be able to combine it to give us what we started with instead. Does that make sense? Yes, no, maybe. Alright, and like I said, just because this is some indifferent stuff, that doesn't mean we forget about all of the previous stuff that we talked about in chapter 5. So we still have to be able to prove some identities. So if I have cosine of pi over 2 minus x, and I want to prove that that equals sine, which is also our cofunction identity, okay? Where do we want to start? Why? Because it's the more complicated side, alright. So I'm starting with the left. Can I distribute my cosine to the pi over 2 and the x? Why not? That's not how it works. There is not a distributive property for any of our trig functions. So if we don't have a property that tells us we can do that, we can't. But what do we have instead? Our cosine difference formula. Okay, so what are we going to have there? Cosine of pi over 2 times cosine of x. And then I'm going to have plus sine of pi over 2 times sine of x. But what is cosine of pi over 2? 0.
Yeah.
Right? Because remember, it would be halfway in between 0 and pi. And that's where it equals 0 for our cosine. Times cosine of x. And then what is sine at pi over 2? 1. Well, anything times 0 is going to be what? 0. And anything times 1 is itself. So we just end up with sine of x. So therefore, cosine of pi over 2 minus x equals sine of x. And like I said, we could also use one of our sum or difference formulas to help us solve a trig equation. So sometimes we might have to simplify something using one of those before we solve a equation as well. So we still have to know the stuff that we talked about in chapter 5. You can also see some of these identities that have like 3 pi's over 2's or pi's, because those are also going to have sines and cosines that are 0s and 1s, so things end up going away. But, questions on that? Concerns, comments? Alright, well that's all there is.